and sharing my screen and going over here. Yay! We're out of that first unit, the preliminary chapter. Now we're going to look at chapter 1. Chapter 1 involves a few things. We're going to start with a little bit of introduction to the whole Cartesian plane. And then we're going to look at solving linear equations and rational equations. And then we're going to go on from there and do, a bit more in the plane. First homework is due on Friday. It deals with that Cartesian plane. Second homework is due in a little bit because it involves a few different types of equations. I was surprised not everybody took the test over the weekend. Some people took the test and didn't send me work. If you fit in that bill, if you sent me work, most people who sent me work, their grades went up, some by a significant amount, some by not such a significant amount. But if you did not send me work, your grade went down. And so if you fit that bill, if you still have that work, you better submit it in Blackboard before the end of today, or else I'm not going to look at it. So, go ahead.
Is that the problem set you sent me? It did. One of them didn't say test.
I had sent it set in class, and I had thought I had sent an email saying that if you do not have my math lab access, let me show in case there are other folks that fit that bill. If you do not have my math lab access in learning modules content, I put a folder for if you do not have my math.
That's right.
And the test is there. And the homework for this next chapter is all in there, and the next problem set. So rather than having me having to email them to you, you having to ask me, I'm just going to upload that digital paper copy of the homework, that PDF in there, and I will, for quizzes and tests, I will make them like this so that you have to, so that it is timed, and you will have to submit your work into the Dropbox that the rest of the class uses. If you did not know about that, stick around at the end of class and talk to me, okay? Then going back here, did anybody want to look at any old homeworks or problem sets or any of that in terms of going over the test? Let's see if I can do this. If you go into Blackboard as a student, when you go into Blackboard as a student and look at your grades, over here, if you submitted something, when you click on it, there should be something that comes down that tells you, and I apologize, I didn't submit anything, that tells you, it says like attempt and the date. And if you click on that, you should be able to pull up the picture that you sent me with the writing that I put on it as if I was grading your paper. So please take the time, if you submitted your work with Blackboard, in Blackboard, to go through and do that, check the work, and if you have questions, please ask, okay?
I went on your folder and the test isn't on mine.
Talk to me after class, okay? Because it was dated, it was supposed to have been done by now. And so I think it was only available during the timing period where the My Lab test was available. It was supposed to have been taken over the weekend. So talk to me after class and we'll see what arrangements we can make, okay?
Okay, I did the problem set thinking that was it.
No, the problem set is the practice test, this homework. So, and if you're doing the paper copies of the homeworks, please notice the due dates. They're gonna apply to the other work too. So, all right, but that having all been said, please again, look at in the Blackboard grade book, make sure you can access that work that I submitted, or that, the work that you submitted with my annotations on it. Otherwise, today we're going to start looking at, yay, the Cartesian plane. How many of you are familiar with the Cartesian plane? Have any of you heard of the Cartesian plane before?
Nope.
Nada.
I bet you any money if I draw it, you'll all smile and nod and tell me that you know what I'm doing. But give me just a second, okay, guys? I need to put something behind the surface so I can tilt it a little bit. There you go. I give you bet any money that if I draw it, you'll know exactly what I'm talking about. And you just probably never heard of its formal name.
Is it the plus sign like lines or?
It is.
Exactly.
It's a graph.
Yeah, it's a coordinate plane. That we use for graphing. It's actually called the Cartesian plane because it's named after Rene Descartes. Descartes, if any of you ever taken a philosophy class? In a philosophy class, you might have heard of Rene Descartes. He's a famous philosopher and also a famous mathematician. If you ever have the opportunity to take a math history class, it's amazing. Back in the day, so many of the people who came up with, developed so many of the things that are used in higher level mathematics were also philosophers, and they did it more as reasoning than applications. And so much of what they developed did not have applications for hundreds and thousands until hundreds and thousands of years later. So that there's some really amazing folks. Most of the ones that you hear about math history classes, sadly, are European men, but there are people from all sorts of backgrounds all around the world here that did all sorts of amazing developments in math and philosophy at the same time, back before any of it really had practical applications, just looking at the what if. Okay. So when I look at that coordinate plane, these two things that I draw here, can anybody remember what they're called? Begins with an A.
Axis.
Yeah, your axes is plural. You have the x-axis and the y-axis. The x is horizontal. The y is vertical. And at their most basic, the axes are just number lines that are perpendicular and they intersect at a common zero. So x-axis being horizontal, if this is 0, I will be positive going in the right direction and negative going in the left direction. Y-axis will be positive going upward and negative going downward. But they're just number lines that intersect at a common zero and they're perpendicular. They divide the plane into, well, I guess technically 5 regions, but we'll start with the 4 quadrants. And again, was not stated. A plane is an infinite flat surface made of points. Let's add that somewhere, that a plane is an infinite flat surface of points. And that it's infinite is shown by putting arrowheads. Four quadrants. First quadrant is upper right. And then from there, we go around in a counterclockwise direction. So this would be a second, this would be the third, this will be the fourth. I always wondered why counterclockwise? And we're going to see when we get into trigonometry at the end of the semester, we can justify that because we think of angles being drawn with one side here, and as they open upward, they're positive angles. And so an angle opening upward would go around in that direction. So what purpose do those axes serve? What are they used for? Aren't they used to help you locate points with ordered pairs? And the ordered pairs are called the coordinates. It's kind of like, and I sit and I say this and I think, oh my gosh, this is one of those old school things that you guys might be too young to appreciate. Have any of you ever actually pulled out an old-fashioned map or atlas to look something up? Or are you guys all Google Maps and GPS? If you pull out an old school map or atlas, there's something like this along the edge, one's letters, one's numbers, and you can use those ordered pairs to help you locate a street on a map. When I look at the ordered pairs, the first one is the X coordinate, the second one is the Y coordinate. The X coordinate is called the abscissa. The Y coordinate is called the ordinate. And so let's, for example, locate the points. And let's have A be the point 3, 1. So the X value is 3, the Y value is 1. So I'm going to go to 3 on my X axis, 1 on my Y axis, and I look at where the horizontal and vertical lines through those points intersect, and that would locate point A there. So that A is in quadrant 1. Instead, if point B were a point, let's say -2, 2, where would that end up? If I go to -2 on the X-axis and +2 on the Y-axis, it would give me a point somewhere right around here, and B wouldn't be in quadrant 2. Is everybody all right with locating points on the plane? What if I ask you to locate a point C, which has as its coordinates 0, -3? Where would that point fall if its X value is 0? Well, if I go below 0 to -3, wouldn't C over here be on the Y axis? And since it's on an axis, it's not considered to be in any quadrant. Now, if I ask you to locate the point O, which has as its coordinate 0, 0, where would that be?
The intersection of the Y and X.
Yeah, that would be right over here, the intersection of the axes, and O is called the origin. point where the axes intersect. So, how are you folks at plotting points? I think there are some homework questions that ask you to just graph points. There are other questions that ask you to find the coordinates of a point. So let's say I have point D over here. What would you tell me the coordinates of point D are?
4, -2.
Beautiful. And is everybody comfortable with that? If
Yep.
so, we're going to change gears for just a second, and we're going to look at an equation in two variables. And if I have an equation in two variables, a solution is a set of ordered pairs whose coordinates satisfy the equation. So let's look at an example. Let's consider the equation 2x plus 3y equals 1. Is 1, -1 a solution? Are you folks familiar with the idea, if this is my point x, y, what I have to do is I have to substitute 1 for x and -1 for y and check. So that would be 2 times x is 1 plus 3 times y is -1. Does that equal 1? Well, that would be 2 minus 3 or -1, which is not the same as +1. So the answer is no. So let's try some more. Is -1, 1 a solution? And so this time for x, I'll put in -1. And for y, I'll put in +1. And again, the equation was 2x plus 3y equals 1. Does 2 times -1 plus 3 times 1 equal 1? Well, that would be -2 plus 3, or 1 equals 1. And so this one's a yes. But what's interesting is if we have two variables, we might have multiple solutions. Is 2 -1 a solution? And so if I substitute in 2 for x and -1 for y into my 2x plus 3y equals 1, that would be 2 times x is 2 plus 3 times y is -1. We want to know, does that equal 1? Well, that would give me 4 plus -3, or 1 equals 1, and it checks. And so I get a yes. And so I can have multiple solutions. And what happens is an equation in two variables can have an infinite number of solutions. And what's cool is the graph of an equation is the set of all the points whose coordinates satisfy the equation, whose coordinates are solutions to the equation. And frequently, there are infinite solutions. And so in that first homework, you're asked to plot points, but you're also asked to sketch the graph of an equation. Is everybody okay if I turn the page?
Hang on.
Let me know when you got it.
You're good.
Some equations will eventually come up with shorter ways, but right now, to sketch the graph of an equation, we're going to make a table of values. Usually, we'll substitute for X and find the corresponding Y values. So we're going to look at a few examples. First example, let's sketch y equals 9 minus x squared for x from the set -3, -2, -1, 0, 1, 2, 3. And so when I was taught a while ago how to first make a table of values, I'm going to make a column for X. I'm going to put my equation in the middle. And then I'm going to make a column for Y. And so our X values will be -3, -2, -1, 0, 1, 2, 3. And so substituting in when X equals -3, I get Y equals 9 minus the quantity -3 squared. -3 squared is +9. 9 minus 9 would be 0. When X is -2, my equation would be Y minus substituting in -2 quantity squared. That would be Y minus 4 or 5. Then I might have Y equals 9 minus -1 squared. 9 minus 1 is 8. Then I could have Y equals 9 minus 0 squared, which would be 9. Then when I substitute in +1, Y is 9 minus 1 squared, which would be 9 minus 1 or 8. For +2, I'd have 9 minus 2 squared. Remember, we're squaring first, so that's 9 minus 4 or 5. And then I'd have for +3, Y equals 9 minus 3 squared, and 9 minus 9 is 0. And so now if I try to go and sketch these, I'm going to label my axes. And my first point is -3, 0. My second point is -2, 5. My third point is -1, 8. My fourth point is 0, 9. Then I've got 1, 8, 2, 5, 3, 0. And those points satisfy the equation. And if I play dot to dot, trying to make a smooth curve instead of jagged straight lines, I would get the graph of the equation. So this would be the graph of y equals 9 minus x squared. How is that process? Is that something that's with in everybody's prior knowledge, making that table of values? I hope that this is something that you might have done in high school, and I hope that if you did it in high school, you at least made a couple of tables of values by hand and didn't become solely dependent on the table function of a graphing calculator. As we look at this, we also sometimes talk about intercepts. And intercepts are points where the graph crosses the axes. We talk about a y-intercept. And a y-intercept is going to be a point on the y-axis. And so I want to go up and I want to look at my graph. Here, my y-intercept would be the point, let's see, if it's on that axis, won't the x value always be 0? If I were to look at any point on the on the y-axis, wouldn't it always have 0 as an x coordinate? So the x coordinate of a y-intercept is always 0. Instead, if I look for an x-intercept, the x-intercept is going to be a point on the x-axis. And so if I scroll up for a minute and look at that graph we just made, here I have 2 x-intercepts. This first one has an x value of 3 and a y value of 0. This one has an x value of -3 and a y value of 0. And do you notice that they both have a y value of 0? Because again, wouldn't every point on my x-axis have a y value of 0? So the x-intercept will always have a y coordinate of the x-intercept is always 0. So to find my intercepts, I'm going to just substitute 0. To find a y-intercept, substitute x equals 0. And to find an x-intercept, you'll substitute y equals 0. So far, so good. Can I turn the page?
Yep.
So then next, let's sketch the graph of y equals the absolute value of x minus 1. And let's use for our table of values, x equals -2, -1, 0, 1, and 2. Again, I'm going to start by making my table of values. X in the middle, I'll put my equation, y equals the absolute value of x minus 1. And I'll use that to find my y values. If x is -2, y is the absolute value of -2 minus 1. Well, what's the absolute value of -2?
2.
2, and 2 minus 1 is 1. If x is -1, y would equal the absolute value of -1 minus 1, and that would be 1 minus 1 or 0. If x is 0, y would be the absolute value of 0 minus 1, which would be -1. If x is 1, y would be the absolute value of 1 minus 1, which would again be 0. And if x is 2, y would be the absolute value of 2 minus 0. The absolute value of, I'm sorry, minus 1, I apologize. The absolute value of 2 is 2, minus 1 is 1. And so when I sketch this, again, I want to make sure I put those arrowheads on my axes, label x and y, put a scale on each of them. When x is -2, y is 1. When x is -1, y is 0. When x is 0, y is -1. When x is 1, y is 0. When x is 2, y is 1. And now when I play dot to dot, this appears to be a straight line. And then in the other direction, it also appears to be a straight line. And we get this distinct V shape. And if you're graphing something that involves that absolute value, you will always get something along the lines of this distinct V shape. Looking at this graph, if I were to ask for the intercepts, the y-intercept, if it's on the y-axis, the x value is 0, and that would be the point 0, 1. And then for the x-intercept, if it's on the x-axis, the y value is 0. And here I have 2. I have -1, 0, and I also have 1, 0. How's that one? Can I turn the page? Next, I want to sketch y equals 1 over x. And in my table, I'm going to use x equals -2, -1, -1/2, -1/3, 0, 1/3, 1/2, 1, and 2. I'm going to make my table of values, substituting in for x to find y. When x is -2, y would be 1 over -2, or -1/2. When x is -1, y would be 1 over -1, which would be -1. When x is -1/2, y would be 1 over -1/2, which means take the reciprocal. So that's going to give me -2. If x is -1/3, y is 1 over -1/3, and the reciprocal would be -3. If x is 0, y is 1 over 0. What's 1 over 0? Can I put 1 over 0? Can I put that 0 in the denominator?
Is it just a 1?
No, it's totally undefined. Take your calculator, please, and take 1 and divide it by 0. You're going to get an error. If I use +1/3, the reciprocal of +1/3 is 3. If I use +1/2, the reciprocal of +1/2 is 2. If I use +1, the reciprocal of 1 is 1. And if I use 2, the reciprocal of 2, 1 over 2, would be 1/2. So let's see, I want to try to put this in the center here. Drawing my axes. Remembering to label x and y to put a scale on them. When x is -2, y is -1/2. Let's see, 1/2 would be about there. When x is -1, y is -1. When x is -1/2, y is -2. When x is -1/3, y is -3. And it's never going to have a value at 0, but does it make sense that as those fractions get smaller and smaller and smaller, this is going to get more and more and more negative? And it's going to get close to that line. And as x gets more and more negative, once the y values get closer and closer and closer to 0. And then on the other side, at 0, there's nothing. At 1/3, it's 3. At 1/2, it's 2. At 1, it's 1. Oh dear. This stylus and I are not getting along today. At 1, it's 1. At 2, it's 1/2. At 3, it's 1/3. And we get similar shape, but in the positive direction. But what's interesting about this graph is it has no intercepts. It has lines that it gets close to, but it has no intercepts. So the idea of making a table of values to get a graph, everybody all right? Couple interesting examples, looking at a curve in the first one, and we know it's a curve because there's an exponent on x, the V shape that comes from absolute value, and then this interesting graph that comes from y equals 1 over x, so y being the reciprocal of x. Sometimes we're asked to find intercepts without making a graph. If I want to find the x and y intercepts of an equation, let's look at that. 2x minus 3y equals, let's say, 6, without graphing. Well, for the y-intercept, we said again, if we're going to be on the y-axis, we'll know to substitute 0 for x. So that gives me 2 times 0 minus 3y equals 6. Well, that's 0, so that just gives me minus 3y equals 6. 2 times 0 is 0, I apologize, which gives me negative 3y equals 6. And then dividing by negative 3, I'd get y equals negative 2. So my y-intercept is the point 0, negative 2. And likewise, if I wanted to find my x-intercept, for my x-intercept, I'm going to substitute y equals 0. Because again, any point on the x-axis will have a y value of 0. So in my equation, 2x minus 3y equals 6. I'd have 2x minus 3 times 0 equals 6. 3 times 0 is 0. 2x minus 0 is just 2x. So it gives me 2x equals 6. And then dividing by 2, I'd have x equals 3. So my x-intercept would be the point 3, 0. And you're going to find some in the homework that asks you to find the intercepts by substituting in the zeros. To find the x-intercept, we substitute 0 for y. To find the y-intercept, we substitute 0 for x. Everybody all right with that? If so, that's kind of the end of what we're looking at in that section 1.1. So let's go on and let's look at that section 1.2, which starts dealing with solving linear and then moves on to rational equations. And so we're going to say that a linear equation will be a first degree equation. And so if it's a first degree equation, it tells me that the highest exponent is 1, and we don't show an exponent of 1. So it looks like an equation with no exponents on it. We're going to start by looking at a linear equation in one variable. When we look at a linear equation with one variable, it's got one variable, its degree is 1. We can say that it has a general form. of ax plus b equals c, where if x is the variable, a, b, and c are real numbers. A solution is a value for the variable that makes the equation true. And I guess backhandedly, we've been solving some of these linear equations, these first degree equations in one variable in terms of a little bit of what we've been doing in terms of substituting right now, in terms of finding our intercepts, and also in terms of when we were looking for values to exclude looking at those rational expressions. What we want to do is we want to transform it into an equivalent equation. Of the form x equals d, where d is a constant. To do that, we're going to use properties of equality. First, we're going to have an addition property of equality. Is everybody all right if I do a little bit of abbreviation? And I'm going to write it symbolically. Addition of property of equality says that if I have an equation, let's say A equals B, then A plus C will equal B plus C. And that's a shorthand way of writing that I can add the same quantity to both sides of an equation and it remains equal. So for example, if I have x minus 2 equals 5, to get the x alone, to isolate the x, is everybody all right with the idea that I'd have to somehow get rid of that minus 2? And I do that by adding the opposite, positive 2. But whatever I add to one side, I have to add to the other. Kind of get OCD, I like to make sure that I put an equal sign in between so that I'm lining up my equal sign so that I'm positive I'm doing the same thing to both sides. Some people don't do that and they accidentally add the same thing twice to one side and not at all to the other. And so this would give me x equals 7. Straightforward enough? Then there's the subtraction property of equality, which I guess is just a special case of the addition property where we'd be adding negative numbers. So if A equals B, then A minus C will equal B minus C. Or I can subtract the same quantity from both sides and it remains equal. And so if I look for an example here, I might have something like y plus 6 equals -4. And if I'm trying to solve for y, to isolate the y to get it alone on one side, I'd have to move that plus 6. And I do that by adding the opposite, -6. Or we can think of that as subtracting 6 from both sides. 6 minus 6 is 0. I do not need to show that addition by 0. So I'm left with y equals on the other side, -4 minus 6 would be -10. That one all right. If so, next we have a multiplication property of equality, which says if I have two equal quantities, if A equals B, then I can multiply both sides by the same quantity. So I'll say A times C is equal to B times C. But if we want to do that, we want to make sure that C is not 0. We don't want to multiply both sides of an equation by 0. It would have the net effect of just getting rid of that variable. So when might I want to use that multiplication property of equality? If I look at an example, let's say I have 2/3 x equals 4. Well, I want to get that x alone, and so I have to undo multiplying by 2/3. Well, are you folks familiar with the idea that if the coefficient on the variable is a fraction, what we're going to end up doing is we're going to multiply both sides by the reciprocal. What do I mean by that? The reciprocal of 2/3, we had said previously when we talked about multiplicative inverses, was 3/2. If I multiply one side by 3/2, I have to multiply the other side by 3/2. Here, when I take this product, I would have 6/6x, or just 1x. Here on the other side, I'd have 12/2, which would be 6. And so if you have a fractional exponent, I'm sorry, I apologize, if you have a fractional coefficient, in order to isolate that variable, if you have a fractional coefficient, you want to multiply both sides by the reciprocal of that coefficient. And let's see if we can fit one more in here. Let's see if we can fit the division property of equality, which says that if A equals B, well, then I can divide both sides by the same quantity and it remains equal. Again, that's only true if I'm not dividing by 0. So for example, if I have an equation like 5x equals 2, I'm multiplying my variable by 5. So to isolate the variable to get it alone, I'm going to divide both sides by that coefficient. 5 divided by 5 leaves me with 1x, which is just x. And my solution would be that x equals 2/5. Does this all look familiar, folks? Is this all right? Am I going too fast? Am I going too slow? Are we doing okay?
We're good. I hope.
So those are the properties that we use to solve an equation. Because they aren't always in such neat forms, the first thing that we want to do is we want to simplify each side as much as possible. If you simplify first, it makes your life simpler. Simplify, 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 simplify. Then if we're solving for the variable, the next thing we're going to do is we're going to use the addition or subtraction property to get all the variables on one side of the equation. Then, and only then, we're going to use the addition or subtraction property to get all the constants on one side. Plain old numbers without a variable. Then we're going to use either the multiplication or division property to get a coefficient of 1 on the variable. And then we'll have our solution, but we always want to check in the original equation. You folks want me to wait a minute, or can we start looking at examples?
Give us a minute.
Okay. Hopefully we get 5 examples in.
Yeah,
Ready?
yeah.
First example. Let's solve 6x minus 3 equals 63. First of all, can I simplify on the left? If I just look at the left-hand side, do I have any like terms or parentheses or anything like that? No, I think it's simplified. If I look at the left, so everybody see on the left, I only have that one constant. So there's nothing to simplify there. I want all the variables on one side, but since there is just one variable, it's on one side already. So then I want to take the constants and move them to the other side. Here my constant is the minus 3. And so I'll add the opposite to both sides, leaving me with 6x plus 0 equals 66. And then that coefficient is 6. To turn that coefficient into 1, we'd have to take 6 and divide it by 6. And again, if I divide one side, I have to divide the other. And so this leaves me with 1x equals 11. And so when I do my check, I want to go back to that original equation, 6x minus 3 equals 63. I'm going to substitute what I'm hoping my solution is for the variable and see if it does give me a result of 63. So that gives me 6 times 11 minus 3. Does that equal 63? Well, that would be 66 minus 3, or 63 equals 63. And it checks. That one all right? Next example then. Let's look at I'm sorry, I miswrote, skipped one. Let's look at 5x minus parentheses 2x minus 10, close parentheses, equals 35. I'm going to rewrite it. In case somebody's not here, they can kind of see what we've done from the original equation. As I look at the right-hand side, I've just got a constant. I can't simplify that. As I look at the left-hand side, I've got those parentheses. I can't combine what's inside the parentheses. And so this is where I'm going to distribute that negative sign. And remember, if there's subtraction, I want to put that 1 in there, so I remember to distribute a -1. -1 times 2x would give me minus 2x. -1 times minus 10 would give me plus 10. So that leaves me with 3x plus 10 equals 35. All the variables are on one side. Now I want to move all the constants to the other. So I'm going to subtract that 10 from both sides, giving me 3x equals 25. And then to get that coefficient of 1, I'll divide both sides by 3. And my solution is x equals 25/3. Don't be afraid if your solutions are fractions. If you do have a fractional solution, they'll usually ask you to express your solution as an integer, which means a positive or negative number, or a ratio of integers in simplest form, which just means a reduced fraction. You want to leave it usually as that fraction, not change it into a mixed number, and not change it into a decimal. Oops, I moved that too quickly. Everybody okay with that one? That next one, let's look at 2 parentheses, 2x minus 1, close parentheses, plus 3 is equal to x minus 3, parentheses, x plus 1. Again, I'm going to rewrite it so people can see the starting equation. If anybody's looking at the notes, that's not here. And again, usually before I do anything else, I look at one side. So let's just focus over here on the left-hand side. It looks like there's work to be done. It looks like I can simplify things. Inside those parentheses, I don't have like terms. So I'm going to distribute. That gives me 4x minus 2 plus 3. And now I do have some like terms. Minus 2 plus 3 would leave me with 4x plus 1. On the other side, again, I have parentheses. I can't combine what's in the parentheses, so I'm going to distribute, but please be careful. We're not just distributing 3, we're distributing the entire -3. So that gives me x, -3 times x is -3x. -3 times 1 is -3. So that gives me -2x minus 3. Now, this one has a variable on both sides. And we said the first thing we want to do is get all of the variables together. If there's a variable on both sides, to get them all on the same side, we're going to use that addition property of equality. I find most people prefer positive numbers. If you prefer positive numbers, you're going to move the smaller of the two variable terms. -2 is smaller. So I'll add 2x to both sides. That gives me 6x plus 1 equals -3. Now we want to move all of the constants, the plain old numbers, together. I'm trying to get the variable alone. I've got to move that plus 1. And I'll do that by subtracting 1 from both sides. Gives me 6x equals -4. Then I want to make that coefficient 1. To do that, I'll divide both sides by 6. And that gives me x equals -4/6, which will reduce to -2/3. How's that one? Any questions? If not, I'm going to give you folks an example to try. Next example. I'm going to have 5x plus 9 equals 9 times x plus 1 minus 4x. I'm going to be quiet for a minute and ask you folks to just simplify the two sides. Could everybody simplify that right-hand side to get 5x plus 9?
Yeah.
Now we're going to get all of the variables together on one side. So I'll subtract 5x from both sides. And that leaves me with 9 equals 9. Oh dear. Do you notice that there's no variable left? If there's no variable left, I have to look at the statement. 9 equals 9. Does 9 equal 9? Is that true? Yes. And so if there's no variable left and what remains is a true statement, I have what's called an identity. An equation. Oh, I'm sorry, you guys. An equation that's true. That's always true. For all variables, you would substitute, all values you would substitute for the variable. Since it's always true, the solution is all real numbers. And again, you're going to get that identity if there's no variable left and it gives you a true statement. So I think we've got 3 minutes. It's going to give me enough time for one last example. What if I have 3 times x plus 2 in parentheses is equal to 7 plus 3x? If I go to simplify here, distributing, I get 3x plus 6 equals 7 plus 3x. I've got variables on both sides, so let me subtract the 3x from both sides, leaving me with 6 equals 7. There's no variable left. And does 6 equal 7? I don't think so. That's a false statement. And so this is considered an inconsistent equation. If it's inconsistent, it has no solution. The solution set is empty. We can show that as the braces with nothing in it. Or sometimes you see this symbol for the empty set there. And again, if there's no variable left and we have a false statement, that's when we're inconsistent. All right. This idea, though, of solving these first degree equations, is that something within everybody's experience, solving an equation?